Seismic tomography has shown us that two large zones of low shear velocity appear beneath the African and Pacific plates, originating at the core mantle boundary. These regions were initially termed superplumes, where anomalously hot, buoyant material is rising through the mantle, expanding into a mushroom-like head beneath the lithosphere. This idea, however, has proven far too simplistic as our understanding of lower mantle dynamics has evolved. This has been centered on our changing interpretation of the D double prime seismic discontinuity. This discontinuity has previously been interpreted as a simple slab graveyard, with shear velocities increasing in response to cold, dense remnants of subduction and chemical heterogeneities produced by slab recycling. In one early model, the slabs form an insulating layer, trapping and building up heat, then erupting into a superplume. This mechanism of formation would suggest that superplumes are a relatively short-lived event, ceasing once the heat has been expended. Since then, the D double prime discontinuity has been reinterpreted as a phase change from perovskite to a more dense post-perovskite. This reaction is exothermic, potentially destabilizing the thermal boundary layer at the base of the mantle, giving rise to a large number of small weak plumes that subsequently converge into a superplume. However, there is growing consensus that the low velocity zones can be attributed instead to static thermochemical piles as opposed to time-variable thermal anomalies. In response, we now refer to them as large low shear velocity provinces, or LLSVPs. Instead of convecting upward, these provinces are representative of isolated reservoirs that remain at the core mantle boundary. Recent research has proposed that the formation of LLSVPs is tied to an additional phase change near the core mantle boundary. The disproportionation of perovskite here produces two distinct phases, a magnesium-enriched post-perovskite phase and a new iron-enriched H phase. If segregation of these can occur, the LLSVPs may represent accumulations of the H phase. The greater iron content can account for both the observed decrease in seismic velocity and a higher density that would be required to prevent the thermally buoyant region from rising. Post-perovskite would then represent the D double prime layer, which also incorporates the slab graveyard. This would therefore explain why the D double prime layer does not appear to exist under the LLSVPs, as they are in fact two chemically distinct regions. Paleomagnetic reconstructions of the eruption sites of large igneous provinces from the last 300 million years show a strong correlation with the surface projected margins of the LLSVPs. In a number of models, these margins have been identified as steeply sloping regions where the horizontal temperature gradient increases. This potentially tells us two things. 1. Plumes are preferentially generated at their margins and are the source of the voluminous flood basalts of large igneous provinces. 2. These regions are stable over geological time. Given that LLSVPs are chemically isolated, material must be sourced elsewhere in the lower mantle to supply plume upwelling. Material that is pushed ahead of the subducting slab is heated in the lowest few hundred kilometers of the mantle via conduction from the core. This material is less viscous relative to the surrounding lower mantle, but is still quite dense, hugging the core mantle boundary. The downward force of the slab acts as a broom, sweeping the material along the boundary. When this comes into contact with the steep margins of the LLSVP, it is forced upwards. This form of edge-driven convection produces thermal instabilities, initiating plume formation. Therefore, the location of subduction in 3D space will determine where along the margin the plumes will form. This explanation reinforces the idea that LLSVPs are static thermochemical piles. The likelihood that LLSVPs are variable and the correlation between large igneous provinces and the margins of these piles are a mere coincidence is very low. However, much of this new research is just that, new, and has not been thoroughly tested and confirmed. For example, perovskite disproportionation should theoretically show up in seismic imaging, and yet it does not. Like with any new scientific research, take it with a pinch of salt and a healthy dose of skepticism.